Boundary condition quantum mechanics, or BCQM, begins without the standard assumptions of physics. There is no continuous background manifold, no ticking coordinate time, and no primitive mass parameter at the foundational level. The universe is instead modeled as an event graph. The base primitives are realized events and the directed edges connecting them, generated by complex propensity kernels. These are limited by a finite coherence horizon, or WCO, a memory constraint that dictates how far into the past the system looks to determine its next state. Chains of these realized events form one-dimensional sequences called threads. Earlier simulations in BCQM 3 and 4 demonstrated that isolated threads exist in a diffusive inertial noise universality class. They exhibit an inertial noise scaling exponent of beta approximately equal to 1/2, meaning their motion is inherently jittery and erratic. Because mass and geometry are not programmed into the graph, they must be rigorously derived as macrostates that emerge from these chaotic threads. The force that organizes this chaos is lockstep. This is the degree to which independent threads align their direction and timing. Lockstep organizes the event graph into a three-tiered hierarchy. At the base, single threads are noisy and lack persistence. The middle tier binds threads into local bundles, serving as matter candidates. At the top, Lockstep forms a massive, globally synchronized bulk. The BCQM framework treats the observable features of the universe as a direct consequence of where a system sits within this specific hierarchy of synchrony. Single threads are subject to intense random walks, which makes them poor local clocks. They possess an operational clock quality, or Q, of order unity, meaning their ticks are indistinguishable from random noise. Creating stable structures requires suppressing this center of mass noise by mathematically forcing threads to bundle together. To study this, BCQMV uses glue axes, phenomenological controls added to the hop kernel that simulate different ways threads can correlate. The first axis is shared bias. It tilts the hop propensities of threads toward a common direction, which forces their paths to align and suppresses random reversals. Shared bias effectively creates directional, pointer-like motion, but it does not achieve precise timing synchronization between the threads. Timing is addressed by the second axis, phase locking. Phase locking couples the internal variables so threads oscillate in step. This increases the bundle's operational clock quality, or Q clock, without forcing it to become a perfectly rigid structure. While shared bias and phase locking organize threads into local clumps, they are not enough to generate a globally rigid spacetime background. The third axis, domains, assigns large populations of threads to regions that share similar effective kernels. This is modulated by the final, highly sensitive axis, cadence disorder. Cadence disorder introduces microscopic timing variance into the preferred hop intervals of individual threads. In this model, cadence acts like a temperature. Depending on the other active axes, it can either sharply focus the timing of the ticks or smear them into a blur. Combining cadence with shared bias produces stiff bundles with low clock quality, resembling simple particle-like structures. Conversely, combining cadence with phase locking yields clock-like bundles with high precision that remain mechanically soft. There is an intermediate bundle size, N star, where combining bias, phase, and cadence creates a sweet spot. These bundles are simultaneously stiff and highly clock-like. By adjusting these mathematical controls, the same event threads can be pushed into entirely different phenomenological universality classes. We can validate these theoretical combinations by looking at the Stage 1 simulation data from BCQMV. This chart tracks the instantaneous lockstep length, or L-lock, the number of hops a bundle stays aligned before decorrelating. The single-axis A-series runs consistently show weak to moderate lockstep. However, there is an exponential jump in the C-series runs. The data shows that reaching the extreme lockstep persistence required for higher-order structures mathematically necessitates the combination of phase locking and cadence. This numerical data enables a precise mathematical definition of inertia in a pre-geometric universe. Effective mass, or MF, is defined via an inertial noise mapping. It is inversely proportional to the amplitude of a bundle's center of mass noise. The more a bundle's stiffness suppresses this noise, the higher its effective mass. In BCQM, mass is not an inherent property. It is a statistical measure of a bundle's resistance to the background random walk. The C-series simulations revealed a specific tension. Certain glue combinations created bundles that were too stiff to represent matter. Treating these hyper-stiff bundles as particles would imply a surrounding background that is mathematically rigid beyond what we observe in the physical world. BCQM v5 identifies the most rigid, persistent lockstep patterns in the simulation as the emergent proto-spacetime background. This dominant population of threads, synchronized by hop coherence and weak domains, forms the vacuum itself. Matter is then defined as a soft-in-rigid defect. These are local bundles with high clock quality but finite stiffness, existing within that rigid background bulk. Particles are regions where lockstep binds threads together at a threshold that is noticeably weaker than the surrounding spacetime. In this view, particles and the vacuum are simply different phases of lockstep within a single, unified event graph. We can extract time from this synchronized bulk by using its aggregate ticks to define a coarse-grained time parameter, tau. The softer defect bundles, the matter, navigate across this tau parameter. In a macroscopic view, these defect trajectories appear as massive world lines approximating geodesic motion. This Stage 1 lockstep mechanics provides the rigorous bookkeeping necessary to describe the world before we introduce the full dynamics of gravity. By showing that mass and spacetime share a common origin in lockstep statistics, BCQMV identifies the specific variables, bundle densities and glue strengths, that will source geometric curvature in the next stage of the program.